Okay, so in this problem, we're told to calculate the effective value of g, the acceleration of gravity, at A, 6,400 meters, and B, 6,400 kilometers above Earth's surface. So I went ahead and drew what we have here. So basically, we have the Earth here, and they're basically picking 2 points, 6,400 meters above Earth's surface, and then 6,400 kilometers above Earth's surface. And essentially, what we're trying to find is Earth's gravity at these 2 points. So the acceleration due to gravity here, and then the acceleration due to gravity at these 2 points. I know it's not necessarily accurate because kilometers are way bigger than meters, but it does well just for the demonstration. And so what we want to find is acceleration due to gravity at this point and this point. And so how are we going to do this? So there's a few formulas you need to know. So first, you need to know that the force due to gravity between any two objects, or the force due to gravity experienced by these two objects, is going to be equal to g times m1 m2 divided by r squared. So this is the formula that is going to, so let me explain this. So m1 and m2 are basically the mass of two objects. So imagine we have an object here and an object here. R is going to be the distance between them. G is just a constant. So the force due to gravity that these are going to experience as a result of the other one is going to be this formula right here. And so why this matters is essentially the object here is going to experience gravity due to this object. So basically, we just need to rework this formula based on the Earth. So notice we're solving for acceleration though, and not force, right? So you should know F equals ma. So if we divide this by one of the masses, so basically what I'm saying is mass 1 and mass 2, you want to imagine one of the masses as the Earth and one of the masses as our example object. That is, we're trying to find the acceleration that it's going to experience. So imagine m1, we'll just say m1 is an object here, and m2 is the Earth. So if F of g is the force due to gravity experienced by that object, then it would just be a times m1, because m1 is that object, the mass, right? F equals ma. Let me rewrite it as this. Is going to be equal to g m1 m2 over r squared. So if we wanted to solve for the acceleration experienced by this object, just you notice the m's cancel. So the acceleration due to gravity, right, is going to be g m g times m over r squared. And so what is r? R is the distance between the two objects. And so generally you take the center of the object, so basically the distance from here to here for the first one. And then m2 is the mass of our second object. So this is how you derive the formula for it. So the acceleration experienced by a planet, right, or experienced by an object as a result of a planet, in this case the Earth, is going to be g, which is the gravitational constant, multiplied by the mass of the planet divided by the radius squared, right, the radius of the planet, or essentially the distance between the two. So normally it's just the radius of the planet because you're standing on top of it, but in this case we're going to be farther out, so this radius is actually going to change. So this is the formula right here. There's a few things you need to know, obviously, to solve this. You need to know g, you need to know mp, and you need to know r for the specific scenarios. Because g and mp, they're just constants. The gravitational constant g is going to be, or it's equal to, 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared. That's the gravitational constant, just a constant value like that. And then the mass of the planet, in this case we're dealing with Earth, so it's really just the mass of the Earth here. And you should know the mass of the Earth, or a value you need to memorize for this chapter, is 5.97 times 10 to the 24 kilograms. So g and mp, they're constant values. And now we just need to find the radius in between right, our two things. So we're trying to find the acceleration due to gravity at this point. Radius is the distance between them. But as I said before, we take the distance from the center to that point. So really, it's this entire distance here. So notice we have the radius of the Earth here, and then we have to add the 6,400 kilometers. So our value r is going to be 6,400, or sorry, I meant meters for this, since first one is just meters, plus the radius of the Earth, which is just it's just a constant value, which is 6.38 times 10 to the 6th meters. So r equals, I guess you could just say h is the height above it plus re. So if you go ahead and do this, let me plug it in. 6.38 times 10 to the 6th plus 6,400. Yeah, so you'll get 6,386,400. And so keep in mind this is going to be in meters. And now we have r, right, the radius or the distance between the two objects. We have the mass of the planet, and we have g. So all is just a matter of plugging it in now. So g, as I said before, is 6.67 times 10 to the minus 11. You're multiplying that by the mass of the planet, which is 5.97 times 10 to the 24. And then you'll divide that by the radius, which we just found, 638,6400. Keep it in meters, and then square it. So let me calculate this. 6.67 times 10 to the minus 11. And then you're multiplying that by 5.97 times 10 to the 24. And then you're dividing by 638,6400. And then you're squaring that. And you will get A, or the acceleration due to gravity at this point, is 9.7631. So you can just say 9.7, what did I say, 9.76. And then the units are going to be meters per second squared, since we're dealing with gravity. So notice that the value is actually pretty close to what we would expect, because we know on Earth it's just 9.8. So it doesn't really change even though you're out so far. So just keep that in mind. So this is your answer to A. So basically still 9.8. And then we'll do B now. And keep in mind, A equals GMP over R squared. G and MP are constants again. For R is the only thing that changes. So instead of using 6,400 kilometers here to get this height, we have to add, or sorry, 6,400 meters. We just add 6,400 kilometers. But yeah, so it's going to be equal to the radius of the Earth. Let me do that. So R equals radius of the Earth plus 6,400 kilometers. So radius of the Earth is 6.38 times 10 to the 6 meters plus, and then 6,400 kilometers is just 6,400 times 10 to the 3 meters, right? Because there's 1,000 meters for every kilometer. So 6.38 times 10 to the 6 plus 6,400 times 10 to the 3. So you will get, let me write this out, 127800000. Obviously, this is in meters still. We're using meters here. And then now it's just a matter of plugging it in again. So let me zoom out a bit. So G is 6.67 times 10 to the minus 11. And then 5.97 times 10 to the 24. And then you have, what is it? You have 1278000. So let's go ahead and plug this in. 6.67 times 10 to the minus 11. Keep in mind this value is squared. Forgot to write that there. So 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. And then you're dividing by 1278000. And then that value is squared. So this one actually is going to be much less. So you'll get let me write it out here. 2.438, so about 2.44, and then the units are meters per second squared since we're solving for acceleration. But notice this value is actually way less, right? So the acceleration, since we're so much farther out, the farther you get out, obviously the more acceleration is going to decrease, right? That intuitively you should know that, but you can see that by the greater the value of the radius, the smaller this value will be, since the denominator is increasing. But yeah, so 2.44 meters per second squared, that's your answer to B. And then A, basically still 9.8, 9.76. But yeah, so basically still 9.8, doesn't really have an impact on it. But here, you should notice that it actually does. So these are going to be your answers, and hopefully you found this video useful.